A normal solid-state drive has one job: store data. It receives files from the computer, places them inside flash memory cells, and returns them when requested. The controller organizes the traffic, corrects errors, and tries to keep the drive alive as thousands of writes gradually wear down the NAND. But a Chinese memory company believes the SSD should do much more than move data from one place to another. Longsys has introduced a 5-nanometer chip called the WM8500. The company describes it as an SPU, a storage processing unit. And according to Longsys, this chip can compress data inside the drive in real time, without requiring the host processor to handle the work. Across text, source code, databases, and similar workloads, the company reports an average compression ratio of approximately 2:1. That creates an extraordinary possibility. A drive containing 128 terabytes of physical flash could provide as much as 256 terabytes of effective storage. No additional NAND package, no second SSD, no magical new memory cell. The same physical drive simply stores certain data more efficiently. But capacity doubling is only the beginning. Longsys says the SPU can also move selected AI data out of expensive DRAM and into high-speed storage, reducing memory requirements by nearly 40% in one tested scenario. The company has even demonstrated a system built around AMD's Ryzen AI Max Plus 395, running a 397 billion parameter model locally. That sounds almost impossible for a compact machine. Yet the idea behind it is surprisingly simple. Instead of treating storage as a passive warehouse, Longsys wants the SSD to become an active participant in computing. The drive does not merely hold the data, it compresses it, sorts it, predicts when it will be needed, and in some cases, acts as an extension of system memory. If the technology works as described, the future SSD may not be measured only by how many terabytes it contains. It may be measured by how intelligently it uses every byte. The storage problem. AI created. For years, computer performance was discussed mainly in terms of processors. Faster CPU, faster GPU, more cores, higher clock speeds. But artificial intelligence has exposed a different bottleneck: memory. A large AI model may contain billions or hundreds of billions of parameters. Each parameter represents a numerical value learned during training. To run the model, those values must be stored somewhere and moved repeatedly into the processor. The calculations can be fast. Moving the data is often slower. Imagine owning a factory with thousands of extremely powerful machines. The machines can assemble products at incredible speed, but every component is stored in a warehouse several kilometers away. The machines spend less time working than waiting for deliveries. That is the AI memory problem. High-end data centers attack it with massive amounts of high-bandwidth memory, large pools of conventional DRAM, and extremely expensive storage systems. An ordinary PC cannot do that. Even a powerful workstation may have 64, 128, or 256 gigabytes of memory. A large model may require far more. So developers use a technique called offloading. Part of the model remains in fast DRAM. The rest is stored on an SSD and loaded only when needed. This makes larger models possible, but it introduces another problem. SSDs are much slower than DRAM. If the wrong data is requested at the wrong moment, the processor must wait. Longsys is trying to reduce that delay by making the drive itself more intelligent. From SSD controller to storage processor, every SSD already contains a controller. The controller translates commands from the computer, decides where data should be written, manages bad memory cells, and performs error correction. Without it, NAND flash would be difficult to use reliably. But the traditional controller is largely a traffic manager. It moves data. The WM8500 is designed to process data too. Longsys says the SPU combines a conventional storage control engine with an intelligent processing engine on the same chip. That distinction matters. A normal controller asks, "Where should this file be placed?" The SPU can ask additional questions. Can this file be compressed? Is it used frequently? Should it remain close to the processor? Can part of it be moved into a cheaper region of the drive? Will the system need it again soon? The company calls the software layer controlling these decisions ISA, or Intelligent Storage Agent. The SPU is the muscle. The ISA is the planner. Together, they turn the drive from a passive destination into something closer to a data assistant. The idea resembles what happened to graphics cards. A GPU was once a specialized component responsible mainly for drawing images. Over time, it became a general computing engine used for science, simulation, and artificial intelligence. Longsys is suggesting that storage controllers may follow a similar path, not by replacing CPUs or GPUs, by performing the data management work those processors should not have to do. How 128 terabytes becomes 256 terabytes. The headline number comes from lossless compression. Lossless means the original data can be reconstructed perfectly. Nothing is thrown away, nothing is blurred, nothing is approximated. A photograph saved as a low-quality image may use lossy compression, where some visual information is permanently removed. That can reduce file size dramatically, but the original cannot be recovered exactly. Lossless compression works differently. It searches for repeated patterns and replaces them with shorter instructions. Suppose a document contains the word semiconductor 10,000 times. Instead of storing every letter 10,000 times, a compression system can store the word once and then record where it repeats. The file becomes smaller. When it is read, the system reconstructs the full version. Longsys says the WM8500 performs this process directly inside the storage device. The computer sends data to the SSD. The SPU analyzes it. Compressible data is reduced before being written to flash. When requested, the SPU decompresses it before returning it to the host. To the operating system, the process can appear transparent. The user does not need to place files inside an archive manually. The drive handles it automatically. With an average 2-to-1 ratio on suitable workloads, 1 physical terabyte can store approximately 2 terabytes of original information. That is how 128 terabytes can provide up to 256 terabytes of effective capacity. But the phrase suitable workloads is essential. Not all data compresses equally. The files that refuse to shrink. Text compresses extremely well because language contains repetition. Source code also contains repeated words, structures, commands, and symbols. Databases may contain recurring values, empty fields, and predictable patterns. These are the kinds of workloads Longsys highlights. Video is different. Modern video files are already heavily compressed. A movie encoded with an efficient codec has already had most of its obvious redundancy removed. Trying to compress it again may save almost nothing. The same applies to JPEG photographs, compressed archives, and many encrypted files. Encryption deliberately makes data appear random. Random-looking data contains fewer predictable patterns for a compression engine to exploit. So a 128 terabytes drive will not always behave like a 256 terabytes drive. One user may see close to the full 2-to-1 benefit. Another may see only a small improvement. A data center filled with text logs, program code, and database records could benefit greatly. A media archive filled with compressed movies may not. This is not a flaw unique to Longsys. It is a basic limit of compression. You cannot repeatedly squeeze information forever. Eventually, the obvious repetition disappears. That is why the most honest description is not, Longsys created a physical 256 terabytes SSD. It created a 128 terabyte storage platform that may hold as much as 256 terabytes of uncompressed source data under favorable conditions. Still impressive, just not magic. Why put compression inside the drive? Computers have compressed files for decades. Operating systems can compress folders. Databases use compression. Servers use software tools to reduce storage needs. So why build dedicated compression hardware inside an SSD controller? Because compression requires computation. If the CPU performs it, processor time is consumed. Data must move through system memory, power is used. Other programs may slow down. A dedicated engine can perform the same task more efficiently. Think of a restaurant kitchen. The head chef can wash every plate personally. But that is probably not the best use of the most valuable worker in the building. A dedicated dishwasher handles the repetitive task while the chef focuses on cooking. The SPU attempts to do the same for data. The CPU and GPU focus on applications and AI calculations. The storage processor handles compression, caching, and movement. Longsys claims the process introduces no meaningful performance penalty. But that is one of the areas where independent testing will be important. Compression always requires work. The real question is whether the 5-nanometer engine can perform that work fast enough that the user barely notices. If the drive can compress at full interface speed, the savings could be substantial. If compression slows sustained writes or increases latency, the value becomes more complicated. Capacity is not useful if access becomes painfully slow. The 5nm chip at the center, the WM8500, is manufactured using a 5nm process. That does not automatically make it revolutionary. Process node names are not direct measurements, and a smaller node does not guarantee better architecture. But 5nm manufacturing provides a practical advantage. More processing logic can fit inside a compact controller while keeping power consumption manageable. Traditional SSD controllers already perform difficult tasks. They manage multiple NAND channels, calculate error correction codes, track wear, translate logical addresses, maintain caches, encrypt data, support PCI Express communication. Now add hardware compression, workload classification, predictive prefetching, and AI data scheduling. That requires more transistors, more processing, more memory, and careful power control. A storage controller cannot behave like a desktop CPU, consuming 100 watts. It lives inside a drive where heat can reduce performance and shorten flash memory life. The 5nm process gives Longsys room to add intelligence without turning the SSD into a small oven. The WM8500 also supports PCI Express 5.0, allowing high-speed communication with the host system. That bandwidth matters because the entire concept depends on moving model data quickly enough to hide the difference between SSD and DRAM. The drive does not need to become as fast as DRAM. It needs to become fast and predictable, enough that software can plan around it. The second trick, using SSD as slower memory. Compression creates the headline. HLC may create the bigger long-term impact. Longsys calls it high-level cache. The idea is to use the SSD as an extension of DRAM. Computers already use virtual memory. When physical RAM becomes full, the operating system moves some data to storage. Historically, this was painful. Hard drives were so slow that a computer using large amounts of virtual memory could become nearly unusable. Modern SSDs are much faster. They are still far slower than DRAM, but the gap can be managed more intelligently. Not all data needs immediate access. Some information is hot. The processor uses it constantly. Some is warm. It may be needed soon. Some is cold. It exists in memory but is rarely touched. HLC attempts to identify those categories. Hot data remains in DRAM. Warm and cold data moves to the SSD. If the system predicts correctly, the processor sees little delay because required data is fetched before it is needed. This resembles organizing a workshop. The tools used every minute remain on the table. Tools needed occasionally sit in a nearby drawer. Tools rarely used go into storage. A badly organized workshop forces the worker to walk across the building constantly. A well-organized one keeps the right objects close at the right time. Longsys says HLC can reduce required DRAM capacity by nearly 40% in a tested 256,000 token scenario involving a 122 billion parameter workload. That does not mean every computer can remove 40% of its RAM. It means this particular architecture reportedly achieved that reduction under a specific AI workload. The 397 billion parameter demonstration. The most eye-catching demonstration involved AMD hardware. Longsys says it jointly optimized an intelligent agent system built around the Ryzen AI Max Plus 395 processor. That AMD chip is designed for powerful local AI systems, combining CPU cores, graphics resources, and a large unified memory architecture. Using the SPU and ISA system, Longsys reports that the machine successfully deployed a 397 billion parameter model locally. That figure requires context. Deployed does not necessarily mean the model ran at cloud data center speed. It does not tell us the exact precision used for the weights. It does not reveal the token generation rate. It does not tell us how much of the model remained in memory and how much was streamed from storage, but it demonstrates the direction. A model too large to fit entirely inside conventional system memory can still run if inactive sections remain on the SSD and are loaded intelligently. Many modern models use a mixture of experts architecture. An MOE model may contain hundreds of billions of total parameters, but only a fraction activates for each token. Imagine a company employing hundreds of specialists. One question requires a lawyer, another requires an engineer, a third requires an accountant. The company does not need every employee in the meeting room simultaneously. The ISA system attempts to keep currently active experts in fast memory while storing inactive experts on the SPU-equipped SSD. When the system predicts that a different expert will be needed, it begins loading that expert early. If the prediction is accurate, the data arrives before the model asks for it. The delay becomes less visible. That is intelligent prefetching. The KV cache problem. Large language models face another memory burden, called the KV cache. As a model processes a conversation, it stores information about previous tokens, so it does not need to recalculate everything repeatedly. The longer the conversation, the larger the cache grows. A short prompt may be manageable. A document containing hundreds of thousands of tokens can consume enormous amounts of memory. Longsys says its system can move older or less active portions of the KV cache onto the SSD while keeping important sections in DRAM. Compression may reduce the space required further. Again, timing is everything. If the model suddenly needs an old section and the data has not been prefetched, inference can pause. The SSD becomes a bottleneck. If the scheduler correctly predicts future needs, the storage delay can overlap with computation. The model continues working while the next data block arrives. This is why the ISA software may matter as much as the WM8500 hardware. A fast drive with poor scheduling is still slow at the wrong moment. An intelligent scheduler can make slower storage feel faster by requesting data before the wait begins. Can this replace DRAM? No, at least not in performance-sensitive roles. DRAM operates with latency measured in tens of nanoseconds. NVMe SSD latency is usually measured in microseconds. A microsecond is 1,000 nanoseconds. That difference is enormous. Even a highly advanced SSD cannot become genuine system memory simply through clever software. It can, however, reduce the amount of expensive DRAM required. This distinction is important. The SPU does not replace the workbench. It makes the storage room more useful. The most frequently used tools remain on the workbench. The rest can move to an automated shelf that delivers them when requested. For AI systems, that can change economics. DRAM is expensive. High-capacity memory configurations increase device cost and power consumption. If a manufacturer can build a system with 96 gigabytes of DRAM that behaves like a larger memory machine under selected workloads, the savings could be meaningful. But the user experience depends on the workload. Interactive applications may be sensitive to small delays. Batch processing may tolerate them. Models with predictable expert activation may work well. Other architectures may not. One benchmark cannot answer every case. Could smart SSDs replace hard drives? Longsys also presents the SPU as a possible alternative to large-capacity hard drives. HDDs remain popular because they provide huge capacity at low cost. SSDs are faster, quieter, and more efficient, but large enterprise SSDs can be extremely expensive. Compression changes that calculation. If a 128 terabytes flash drive stores the same amount of suitable data as 256 terabytes of conventional capacity, its effective cost per stored terabyte falls. It may still cost more than hard drives, but total ownership includes more than purchase price. Hard drives use mechanical parts. They require more physical space. They consume energy. They produce vibration. They need cooling. They may fail differently. An SSD with intelligent compression could become attractive in environments where space, power, and access speed matter more than the lowest possible purchase price. However, flash endurance remains important. Compression may actually help by reducing the amount of data physically written to NAND. If 2 terabytes of original data compress to 1 terabyte, fewer flash cells need to be programmed. That could extend drive life. But only independent endurance testing can show how the complete system behaves under sustained heavy use. The SPU itself also creates new complexity. More intelligence means more firmware. More firmware means more opportunities for bugs. Storage errors are unforgiving. A graphics glitch is annoying. A corrupted database can be catastrophic. The questions Longsys still needs to answer. The company's claims are fascinating. They are not the same as a full independent review. We still need to know the sustained compression speed. Can the controller maintain performance when writing hundreds of gigabytes continuously? How does latency change when compression is active? What happens with data that compresses poorly? How much power does the SPU consume? How hot does the controller become? How consistent is the 2-to-1 ratio across real enterprise workloads? How does the system protect data if power fails during a compressed write? How many drives can operate together in a server? What is the cost compared with a conventional enterprise SSD? And perhaps most importantly, when can customers actually buy one at scale? A technology demonstration can show possibility. A commercial product must show reliability, support, firmware stability, and manufacturing volume. Storage buyers are conservative for a reason. They are trusting the drive with information that may be more valuable than the hardware itself. My take. My view is that the most important part of the WM8500 is not the headline capacity doubling. Compression is useful, but it depends heavily on the data. Some users may approach 2 to 1, others may see far less. The deeper shift is architectural. Longsys is treating storage as a computing layer. For decades, the hierarchy was simple. The CPU computes, DRAM feeds the CPU, storage waits. AI is breaking that arrangement because model sizes are growing faster than affordable memory capacity. The SPU offers another approach. Let the storage device perform part of the data work. Compress information before it consumes flash. Keep inactive model experts outside DRAM. Predict which data will be needed next. Move old KV cache entries into a lower-cost tier. None of those ideas individually eliminates the memory bottleneck. Together, they may make local AI systems far more capable. The risk is that intelligent storage becomes complicated storage. Prediction errors create delays, compression adds processing, firmware bugs create new failure modes, and company demonstrations may look better than mixed real-world workloads. Still, the direction makes sense. We are approaching a point where adding more raw storage and more raw DRAM cannot be the only solution. Efficiency must improve too. A 128 terabytes drive should not merely be a bigger bucket. It should understand how the bucket is being used. That is what the WM8500 is trying to become. Not just an SSD controller, a storage processor, a chip that turns capacity into something flexible, a chip that lets flash behave partly like memory, and under the right conditions, a chip that allows 128 physical terabytes to hold 256 terabytes of original data. The achievement is not that Longsys created storage from nothing. It is that the company may have found a better way to use what was already there. So what do you think? Would you trust a smart SSD that automatically compresses your files and manages part of your AI memory? Or would you prefer a simpler drive with predictable physical capacity and fewer layers of processing? Let me know your view in the comments. And if you want more grounded breakdowns of the chips, memory systems, and hidden hardware reshaping computing, subscribe to Eastern Engine, because the next storage revolution may not come from adding more flash. It may come from teaching the drive what to do with it.